is PROTOS and who am I? PROTOS, we develop software tools, domain-specific languages, modeling tools, and so on, test tools for embedded systems. So we also have a very strong focus on languages and architecture. And who am I? I'm an aerospace engineering who likes embedded software architecture, tests, and tools. And yeah, today we are talking about contract-based design, which is a very nice method to bring robustness into your systems. So let's have a look at the problem we are addressing here. Imagine you're standing at a traffic light with your car, and you start driving, and suddenly in the other direction another car enters the traffic the zone, and you collide. Why? Because both traffic lights are green, so that's a safety risk, of course, a very big one. So that's something you want to avoid. This kind of problem occurs in all kinds of systems, and usually it's not so simple like two lights in a traffic light crossing. So how can we avoid this in complex software and systems? The first question is, how do we describe what we want? So how can we describe precisely what must not occur? Yeah, we can make textual requirements or specifications. For example, requirement 1 is 2 traffic lights must not be green at the same time. Okay, so that's nice, but as human beings we understand this, but how do I prove it? It's not very precise, the description, and it's even more difficult to really prove that my software really fulfills this requirement. So how can I prove it? I can do tests on all levels, unit integration, acceptance test, hill, SIL, mill, hill testing, and so on. But it's also very complex. So the question is, well, testing helps, of course, but isn't there a more elegant way to describe and prove that the system really works the way it's intended to? So testing helps a lot, but usually it's done very late in the process. Most errors are introduced while you're coding or even in the requirement phase. The error detection usually takes place much later in the unit test or in the system test, and so on and so on. And the later you detect an error, the more expensive it gets. And the more dangerous, of course, if you do not detect the error, yeah, you might cause a problem for health of somebody or financial risk or something like that. So we want to know much earlier in the process whether the software works or not. So imagine you could do something like that. You specify what you want, then you build your software, your models, your structure model, behavior model, source code, and so on. And then you define as a formal contract what you really want. Formal in a sense that it's that you can prove it. And then something magical happens, a magical mechanism that verifies your application. So that's basically what contracts are about. And now I'm going to introduce you a little bit how this works. So the classic contracts, as some of you might know, have been introduced by Bertrand Meyer. He designed the programming language Eiffel, and those contracts allow the formal specification of interfaces for functions and classes, so on a unit level, and enable formal or runtime verification. The idea is you define pre and post conditions for every function. You can call invariants and side effects for the class. So what must be given at all times, invariants, or what must never happen, side effects. For example, you must not change a certain variable in this context or something like that. And languages like Ada, Eiffel, and so on have a built-in support for this kind of contract. ADA from avionics systems. Eiffel is not very well known, and in practical use, I guess it's not used very often. So, but ADA is a typical example for this kind of contracts. So how does it work? Let's have a look at the piece of C code. You can implement contracts in C, but you have to implement them. There's no mechanism in C to verify contracts, no built-in support. So for example, you could implement contracts as C code with an assert. For example, a precondition, if you enter the square root function, you check whether the variable is bigger or equal 0. If it's below 0, you would get a division by 0 error of the square root function, for example. That's something I want to avoid. So I have a precondition I check before I even call the meat of the function, so the real implementation of the function. And when I'm done with my implementation here, at the end of the function, I check whether the result I will hand out, I will give back, really also is correct in a sense, or that the post condition really holds what the contract guarantees. So that's a very simple example for a contract. Yeah, so the support in C is not very good. In ADA, this works much better, for example. But a contract on this level has a couple of problems, especially for embedded systems. So it's a very good thing to do, but it only works for synchronous functions and classes on unit level. So within a class context, for example, basically on the level you do a unit test. And it does not help with asynchronous concurrent systems. So it doesn't help on integration or system level, or at least not a lot. So most embedded systems are asynchronous concurrent systems. They have states, they have history, they have certain execution orders, they have timing problems and so on. That's something you cannot really define with this classic contracts. And another problem is this kind of contract-based design is very fine-grained. So to really get a good coverage, you need a lot of effort. You need to make contracts for a lot of functions to really get a good effort. Yeah, but still it's very valuable, but on a lower level. We're looking more on a higher level, on integration level, on system level. We want to protect our systems on that level and make sure that systems interact correctly. And for that, those classic contracts are not very well. So what we do is we move the contracts one level higher. We use state machines as interface contracts because nobody knows what a temporal logic is, for example, for model checking and so on. To make this easier, it's better to use something like a state machine. It's also formal, and from there we generate everything else. So give an example. Imagine you have a programming language like C. It's a very simple example. It's not on system level. It's on unit level, but it's a very simple example just to give you an idea of what I'm talking about. So for example, in this example, you have an initialize function, a start-stop function, and function 1, 2, 3. So now if I ask you, what do I have to do? What do I have to call before I can call function 2? Okay, we could interpret this interface and say you have to call initialize, maybe start, and then you can call function 2. Okay, that's an interpretation, but you cannot be sure about this. Or if I called function 2 and I call stop, do I have to initialize again? To be honest, I don't know. It's not specified here. It's just a syntax. There's no semantics, no order, no timing, and so on. So, but now if I take the same interface and add a semantic specification as a state machine, now I can express what is allowed and everything else is forbidden. That's also very nice. You define what is allowed, everything else is always forbidden. So in this case, if I ask you the same question, what do I have to do before I can call function 2? You have to initialize. You have to start, and then you can call function 2 or 3 or 1. If you stop, you do not have to call initialize again. You cannot call initialize again, actually, according to this contract, but you have to call start again, and then you can call function 2 again, or function 1 or function 3. So that's the idea. Everything else is just not possible according to this contract, or not specified. So what happens now if you only are looking at this contract, and if you compare it with the possibilities, with all the states you can reach by using just the API defined in C. So let's have a look at the combinatorics. Let's assume every call to an API or to a system changes the internal state. Now that's one of the ideas here. So if you are looking at the pure C API and you call every function once in every order that's possible, you theoretically have reached 720 different states in your software. If you protect your software with an interface contract, or if you only do what the interface contract allows, you only have 6 orders of execution. That's much less internal states you have to test, for example. If you do this again, you test not only once, you test twice or 3 times. You already are in depth 3 and are already at something like 10 by the order of 15 possibilities or states, internal states here. Here with the interface contract, you only have 362,000 states. It's a lot, of course, but up to level 2, depth 2, I still can test this completely. So of course I have to do something to really make sure that the contract is fulfilled. But so that's the combinatorics. So first of all, you get a massive reduction of execution paths or internal states by orders of magnitude. A lot of orders of magnitude, actually. And this enables much simpler systems and better testability. And another really nice side effect, you get a very, very effective way to specify your interfaces. So if you give the state machine contract to somebody, he knows what he can do, and he knows what he cannot or must not do at the interface. So only as an interface specification, that already provides a lot of value. So what can I do now with this contract? I have to make sure that my system really works. So first of all, I specify the interface semantics with a contract, and I can generate documentation. So that's a lot of value already, because you always have a consistent and correct documentation, which cannot always be set of all documentations. And so then in the early phases, so you model something, you can make a model check, a formal verification on model level, whether your model, so for example, a state machine or something like that, really holds the contract, really does what the contract promises. So that's a very, very early stage testing. Then the next level would be during test execution. So for example, in a dynamic test phase, unit testing, or also system level or integration level testing, you can generate out of the contract, you can generate test cases that try to prove that your system works, or that try to break your system to prove that it doesn't work according to the contract. That's a very nice technique. And last but not least, a very nice method where you can generate robust interfaces or monitors for runtime verification. For example, the formal verification in the models, you need certain tools to do that. You need a modeling tool to do that, and not all modeling tools can do that. Generating test cases, that's already something that can be done also for manual code. And generate robust interfaces for interface monitoring during runtime. That's something that gives your application robustness during runtime, because you can also test things you did not develop yourself. So for example, if somebody's using your software, it has an interface to your software or to your system, you can make sure that he cannot break your system by generating a robust interface. So those are basically the things we can do with the contract. So now I'm going to make a little demo. I'm going to demonstrate all three methods. First method is a very formal verification and an implementation assistant in one of our development environments we use for embedded systems, or we develop for embedded systems. The idea is you have a structure and a behavior model and an interface specification with a contract. And while you're modeling the state machine, for example, the contract checks all the time whether the contract is fulfilled or not. If it's not, it makes suggestions what you can change. The second demo is contract as a black box test specification. It's called combinatorial state transition tests. We use this for software and hardware in the loop tests, for example. So you define as a state transition diagram all the combinations, all the passes, all the variables, all the variants for variables, and so on, as a black box description. It's very compact, very efficient to describe the combinatorics here. And from there, we generate the test cases, all needed test cases to find certain kind of problems. For example, race conditions, sporadic errors, and things like that. So you describe the black box behavior and you generate the test cases to prove that your system works or to prove that your system does not work. It's a combinatorial test. You do not write thousands of test cases on your own manually, but you can generate them. That's a very efficient way to bring robustness to your system. So that's test level. Then the last example will be, oh, just a second. So we use this, for example, to with our mini hill system to run hardware signal level hardware in the loop tests on your desktop, and we generate the environment simulation and the test cases directly from the models here. So the last example I'm going to show you is the last demo is going to be an interface definition language with contracts and generated runtime monitoring. So now this is the runtime monitoring. In this case for C code, can also be used for other languages. So the idea is you define your interface as an interface definition language. You specify the contract, so all allowed calls and messages and so on. Then you generate the part in the middle here. So the client is calling the service implementation, so your implementation of whatever. But we place the generated contract monitor, including all the interfaces, in the middle here. And it makes sure that no call gets in that's not allowed. So you can really protect your service implementation against misuse or against attacks or whatever it is you want to prove. And in the end, you compile and run your system. And while it's running, it's monitoring continuously what happens here. And if something happens that's not allowed, you get an error message or you get an error handler called, and you also get a very good specification of what actually happened. So for example, here in this case, as a sequence diagram, I know exactly while I'm in processing, start processing is not allowed. So that's forbidden. So I get the sequence diagram to analyze what happened. I need to understand what happened or who attacked me or something like that. So now I'm going to make those three live demos. First of all, the tool tries, it's an implementation, eTries, it's an implementation of the language real-time object-oriented modeling. It's an open source project we run, and here you can, we have, for example, very big machine controls. That's a actual project, customer project I can show. It's in it produces medical devices, so it's FDA certified. So I can double click, go inside. Here I have the RT controller. It's in German, everything here. So I have different modules. You see, it's a lot of components here, and every component can have an implementation as a state machine. So you can imagine that we have a couple of, I don't know, maybe 100, 200 state machines in here, and maybe 600, 700 IO points, external systems we control, motors, measurement devices, and so on and so on and so on. So it's a really complex system, and it's even certified. So we need to make sure that it works. So what we do here is, for example, here we have a protocol to control motor. So for example, I can start a motor to move it to a certain position, and then I expect that a done moved position returns. It's an asynchronous bidirectional protocol. Right? It's an asynchronous software. So, and I also can stop this, and then I get a stopped. But that's only the syntax here. What's more interesting is the contract now. The contract, it's a so-called legal execution tree. It's a form of an interface state machine, can do the same things with it. So when I start to move to a certain position, I expect a done moved position in return, or I can actively stop the motor. Those are the two options. Either I get a done moved position, or I can stop the motor. If I stop the motor, I get a stopped from the motor. So that's the order of execution I expect from all those messages. And if I want to enforce that, I can check my model. And same here, for example, for the timer protocol. You have maybe a lot of race conditions in your software. I'm sure you have. Some of them will never occur. Some of them will, but not very often. So we always create all the protocols with their semantics. So for example, if you start a timeout, either you get a timeout back, so when it's done, or you can kill the timeout, and then it's stopped. So those are the two protocols I want to show you in this example, and I created a little demo here. Demo component. This demo component has two timer ports and one motor port, and behind those, attached to the protocols here, or to the interfaces, are the actual are the contracts. So now I want to edit behavior. I have a little state machine inside this component, and now I say, let's start the motor. So that's a state, start motor. So I, over the motor protocol here, I want to move the motor to certain positions. Okay. So now immediately I get the information. Okay, I did not create a transition for done move to position. I must do this because that's what I specified. I can stop the motor if I want. That's my decision. It's outgoing. But the incoming transitions I need to implement. So I click on this implementation, on this assistant here, and I immediately get a correct implementation. I still could stop the motor. Yeah. So, and now, yeah, let's say now I'm done with my motor, and I want to add a timeout to make sure that the motor is, if it doesn't stop in a certain time, I want to start a timeout to make sure that this is correct. So sorry, timeout. Let's say 1,000 milliseconds. Okay. Oh, immediately I see. Okay, I need to satisfy. I need to satisfy the timeout here. So I satisfy the timeout. So, and the problem is, if the done move to position returns, the timeout is still running. So I might produce a race condition here. So I need either to kill or to satisfy the timeout transition here. So in this case, I, as an implementer, I say, okay, I want to kill the timeout. And now it's satisfied here. And here, in this case, if the timeout comes and I go to the state 2 here, that's an error state. According to my specification, the motor is might still be running. So probably I should stop the motor. So I stop the motor. Motor stop. So now the motor is stopped, but I still need to wait for the answer. And of course, that's a self transition to make sure that I consume it and probably propagate the error and things like that. So that's model level verification. I can be pretty sure that I didn't forget anything regarding timeout and the motor. So if you do this for all the protocols, you reuse this check at every interface you that has the same interface definition. And that's a lot. A lot of components have the same definition here. So that's example one, model level verification. Of course, you need the tools to do that. You cannot do this if you do not have a modeling language that supports this. So next step, test level. I have a little hardware in the loop test system here on my desktop. That's our mini hill. And we are generating test cases here to try to break this chip with its software at the pins of the microcontroller. So typically black box test for hardware in the loop. So now here I have a contract. It's called a state transition test diagram. And now I can say, okay, I want some more data. I want to run the motor also with 1 or with 99% of speed and so on. Here you see the contract changes. And now if I generate the contract, the test cases are generated and also the documentation. And here in the documentation, you immediately see here now I added more test cases also for 99 and for 1% of speed. And if that's not enough, because I want to break my system really bad, I say I add some more metrics, a higher metric, more combinatorial generation. And here, for example, I have 25 test cases, and now I generate this again. And suddenly I have, let's have a look at this. I have a couple of more test cases. So now we have, so it's still billing. So now suddenly we have something like 163 test cases with a lot of more combinatorics. And I might find a lot more race conditions or sporadic errors with those test cases. They run a little bit longer, but on a simulated system, that's not, it's in a range of minutes. So that's a very efficient way to try to break your system, to bring robustness or safety, security, and so on in your system, depending on what you're focusing on and what your test cases actually are. So that's the second example. And now the third example is an interface definition language for, in this case, C code, can also be used for something else. We want to protect C modules, or let's say also bigger chunks of software at the interface level. So we define, we have a C interface definition language, IDL. Here you have, for example, the function initialize, start processing, handle, go to standby, and so on. And here you see the signature of the function, but we can also, in the signature, we can integrate checks. For example, a range check. Those are the classic Bertrand-Meyer contracts, the classic contracts, ranges, side effects, and so on that we can specify here. So that's the classic part, but we can also add an interface state machine that tells me exact, or where I can specify exactly in which order or also with which timeouts certain function calls are allowed. For example, I have to initialize first, start processing, and so on. So now if I let this run, I'll let the contract demo run. So now I don't have any problem. Now I'm going to modify my caller, so the one that calls my protected function. So, and I enter something, for example, while I'm in the processing here, I want to enter start processing, which is not allowed because it's not defined. If it's not defined, it's not allowed. Now I run my system again. So contract is generated automatically, and immediately I get the information that there's an invalid transition for the current state processing with the trigger start processing. And now, since we know exactly what happened, because we're monitoring everything, I get a log as a sequence diagram, and I see exactly that in the processing state, I called start processing. I even can localize this extremely well. That's very valuable to find the actual problem, or to get a log that tells me who attacked me, depending on safety, robustness, security, depending on what you're aiming at. So those are the examples I have prepared. We do a lot more with contracts, and now at the end, I want to tell you what are the typical use cases for this kind of contracts. So we focus on embedded systems, but it also works for all kind of other systems. It's the same technology, basically, maybe another code generator or something like that. So if you want to protect your system at the external interfaces, so for example, you have something you want to protect, a medical device or a middleware in an airplane or a machine control that can be misused from the outside or attacked, then you want to prove that the other system behaves incorrectly. Maybe also your own system corrects not or implementation is not correct. And then you can generate interface monitors directly from the contracts. Another use case is you want to check whether your implementation of complex behavior is correct, and you want to implement faster. That's what I've shown you in the model. On model level, you can use the contracts for model level verification and so model checking, real model checking. And with this implementation assistant, you're really fast and getting it right. You don't even need to verify it or think it through afterwards because it's correct according to the specification. Then another use case is if you have a safety critical system and you need redundant or diverse implementations for the safety monitors. So you have your implementation that's very big, and then you have a couple of constraints or contracts that make sure that your system does not break anything, or that your system is no health risk or something like that. Then you can describe this the rules as a contract and generate safety monitors. They're completely redundant and run them in parallel, redundant or diverse on another chip or wheresoever, to specify the safety rules and generate the runtime monitors to make sure that your system has a redundant monitor in there. That's a common technique. Many of those systems are implemented manually. We generate those redundant monitors. And you also can find bugs that are really hard to detect. So for example, sporadic race conditions that happen at one customer once a year, that's really hard to detect and really hard to debug. So you specify the expected behavior and you generate test cases, combinatorial test cases that try to break your system and try to find out much deeper whether there's something that's not supposed to be. Yeah, and of course there are many other use cases as well. If you have any questions, please let me know. Michael Weiss from Hitex, or also please contact me directly.